All right, this was the last batch. Welcome, everybody. It's our pleasure this morning to host Petar Veličković. Please note the two accents in the name. So if you put them, use the right pronunciation or don't put them. So Petar is doing the pleasure to come today. He holds a PhD in computer science from Cambridge under Petrolio. But you probably know him for the work he did on graph neural networks. He, of course, is one of the person who has pushed this area of research further, in particular his formulation of graph attention networks. But also what I really liked in the last few years is his attention to trying to understand the message passing framework up to a point where it really helped rationalize the way we conceive graph neural net architecture into something that is principled. And in another space, Peter being at DeepMind, he also was involved into big science projects, some of which made the headlines and the cover of Nature. This is not what he's going to talk about today, though.
I will mention it.
You will mention it. He's going to take us to his recent work on neural algorithmic reasoning, and I will let him define reasoning because we had interesting conversations about that yesterday. Peter, the floor is yours.
All right. Thank you very much, Pierre, for the introduction and for the invitation to come here. And thank you all for coming to my talk today. It is a great pleasure to be speaking at EPFL. I wanted to visit for a very, very long time. Finally, an excuse has happened. So, as mentioned, my name is Petar Veličković. I'm a staff research scientist at now Google DeepMind and also an affiliated lecturer at the University of Cambridge. And I'll be talking to you about the area of research that is currently captivating most of my attention and is, in my opinion, one of the areas that could lead to very interesting developments in generally intelligent agents in the near future, as can be witnessed by the slightly controversial title. So let's see what we can say about reasoning algorithmically. First of all, I think it's a good idea to kind of put us all in the same frame of mind about what we're going to be talking about today for a large part. So as the title sort of implies, what we'll be talking about today largely concerns what I like to call classical computation, right? And when I say classical computation, I mean the kinds of computations that you might see during a typical undergraduate degree in computer science, or something that we might have done a lot before deep learning became a big thing. So think things like shortest path finding, dynamic programming, interesting ways to structure data, and so on and so forth. Here I just have a snippet of possible illustrations of such approaches. But of course, because we are talking about all of this in the context of deep learning, we're going to be thinking about how can we take what's very nice about such classical computations and think about how to capture it with neural networks. And this is a very interesting topic to think about even today, because when you think about the kinds of things that our current state-of-the-art models tend to be really bad at, it tends to be exactly the things that these guys tend to be really good at. So if we can bring together these two worlds, this can be truly the spark that we're missing in building these systems. And I think everybody who's like working at the intersection of these fields has their own story that brought them into it. And I felt it was good maybe also to give me a bit of credibility, hopefully, of why I'm talking to you about computation and capturing it, to tell you a little bit about how I came to this entire story myself. And maybe it makes sense to start at the beginning, really. When I started to dabble with computer science, it happened through random tinkering with programming, which shortly after turned into this competitive programming genre, which is basically, 5-hour competitions where you have to write a program that solves some particular problem as quickly as possible using as little memory as possible. And this is me during various stages of my development, participating at various forms of competitive programming at different levels. And eventually it culminated with me being part of this team of competitive programmers from the University of Cambridge, where we actually won the first place on the Northwestern regionals of the ACM-ICPC. So hopefully this gives me a bit of credential to talk to you about competitive programming and algorithmic computation today. And to be honest, these kinds of things, even though I've largely moved on to machine learning research, these things follow me to this day. Recently, we filmed an episode of Machine Learning Street Talk. If you don't follow it, I highly recommend it. It's a very nice series of vlogs. And we talked a little bit about the stuff that I'll be talking to you about today. So there's a new episode coming out soon on the topic of today. So if you find it interesting, do check it out. But as part of filming this episode, the show organizer actually put us on the spot in front of a whiteboard and gave us a lead code challenge to solve. So you can watch me try to struggle with it for about 20 minutes as a video that's already out there, if you find such things interesting by any chance. So, okay, competitive programming and classical algorithms is what originally brought me to computer science, right? And I believe the story is similar for a significant proportion of machine learners at work today. So I never really even considered doing machine learning until the last year of my undergrad, when I wanted to do a bioinformatics undergrad project, because I heard bioinformatics is full of algorithms. So I thought I'd get to do a nice little project that just concerns algorithmic computation. And then my advisor told me, no, don't think about doing any of that algorithmic stuff. Everybody in bioinformatics is doing machine learning now. You should learn machine learning. And I sort of followed what he said, and this turned into an entire PhD in graph machine learning. But I never really forgot the roots. And what I'll be talking to you about today is a story of how I went full circle, taking these algorithmic beginnings and combining them with the graph neural network research that I've done in recent years. So this will hopefully impart some of my views on how these fields have evolved over time. It will introduce this area of neuro-algorithmic reasoning, which is, in my opinion, an emerging and exciting field of research that will become more important in future years. And hopefully it will illuminate some of my own perspective towards how can we use these methods to build more generally intelligent agents in the future. So I mentioned graph neural networks here in this introduction. I will not be talking in detail about graph neural networks in this talk, but I feel like it's useful for us all to be on the same page about what these models roughly are. Just so whenever I name drop GNN or I say a GNN looks a little bit like this, you can sort of see it and say, aha, this is why that is the case. So a graph neural network effectively learns representations on a graph structure, right? So imagine you have a graph with some nodes and edges connecting those nodes. And in each node of the graph, you have some feature vector xi for node I, right? And the graph neural network updates those features from the input space x into some latent space h using this local function f, which takes into account the features of a node and the features of all of its immediate neighbors in the graph, right? And so long as you build this function to be invariant to any permutations of the neighbors, this is a legitimate graph neural network. So whenever I say GNN, I mean something like this, okay? Now, you might be naturally interested about how we actually implement this function f, and there's many possible frameworks to do this, but one of the most general ones is the message passing framework. So here I've zoomed in on the node that updates its features and its immediate neighbors. So what happens is every node collaborates with its neighbor to compute a message vector. So that's what this psi function here is doing. You take the features of the two nodes, you compute a message to be sent across that edge, and then the receiver node combines all those messages together using some aggregation function like addition, averaging, maximizing. Whenever you see O+, it can be any of those things, and then transforms the output a bit more to compute the features. So when I say GNN, I mean an operator that does something like this, okay? Now, naturally, if you haven't heard about GNNs before, you might be interested to know more about them. Unfortunately, this is as far as I'm able to talk about GNNs in this particular talk, just because I have a lot of material to cover. But in case you want to know more about GNNs, I've talked a lot about them. I really like them. I really like teaching about them. And there is a 30-minute long recording of me talking about theoretical foundations of GNNs on YouTube. So if you want to learn about GNNs and use it as additional context after the talk, this is the video I would highly recommend you watch, okay? Now, let's talk a little bit about how algorithms came back into the picture. So after graduating with my PhD in 2019, shortly after I joined DeepMind, and shortly after that, I met Charles Blundell, whom I collaborated with a lot in a lot of the papers we're gonna talk about today. We're both theoretical computer scientists by training, which is very convenient, and we had a lot of really fun early discussions. And there was this one interesting but seemingly not very consequential question that kept being asked in our meetings, which is, could we use these graph neural networks to execute classical algorithms? So when I say execute, what I mean is something like this. Imagine you want to teach a graph neural network model to execute something simple like breadth first search. You give it as input the specification of a graph, which asks you to say, find shortest paths in this graph. You give it a feature that says, what is node 0, the node you start from. Then you feed those input features into a GNN, and it runs the computation that I just showed you in the latent space. And can that GNN then learn to predict what the shortest paths in this graph are, starting from node 0? So the output here is the distances to all of the other nodes, as well as this highlighted edges telling you where the shortest paths are, right? Can we teach a GNN to do this? This was the question we were asking. And I must say, initially, we didn't think much about how impactful or relevant this would be. We just thought of it as a cool way to benchmark how powerful these models are, because there's a lot of very nice things about this task which you don't see in a lot of machine learning problems. First of all, there's infinite data. No problems about the data sets being too small or too big. You can generate any size of the inputs you care about. There's a lot of complex data manipulation happening, going from inputs to shortest paths. A lot of interesting computation happens in the middle. So you're truly benchmarking, is your GNN learning to compute useful stuff? And lastly, there's a clearly specified function that you're trying to imitate, means that you can actually rigorously evaluate some credit assignment. Like, is your model actually reaching the solution in the expected way, or is it hacking the distribution to find something interesting, which is not that useful? But we didn't really think about it from any other more generic perspectives. It was really just an interesting way to benchmark these systems and how well they perform. So the underlying question we were trying to answer then is, what makes a neural network better or worse at fitting certain classes of algorithmic tasks, or any tasks? It doesn't have to be algorithmic, but algorithms are just very nice formalism to study what a task is. And it turns out, concurrently to our efforts, there was this really interesting paper from MIT, which introduced this concept of algorithmic alignment. And here, it basically laid the foundations for how to build a machine learning model to be better at fitting certain classes of algorithms. And here specifically, you can see a direct one-to-one pictorial correspondence between the computations of a GNN, which I showed you before, and the computations of what is known as a dynamic programming algorithm. So something which breaks the problem down into subproblems and then combines the results together, right? This is one specific dynamic programming algorithm, Bellman-Ford, a very popular approach for shortest path finding. You compute your own distance based on the minimum of how to reach all of my neighbors plus traversing the path from the neighbor to myself, right? And every single part of this equation can be mapped to parts of the GNN equation, right? The variables you're optimizing for, the distances to each of the node, line up with node features. The act of adding the edge weight is the message function that you're computing, and the act of optimizing over all the neighbors is the aggregation function, which aggregates all the messages together, right? And this can actually be mathematically formalized. Like, you can prove a theorem, and in this paper, What Can Neural Networks Reason About, published at ICLR 2020, the researchers from MIT proved a theorem that says, if your neural network is better aligned structurally with the algorithm, meaning you can break it down into parts that line up with the parts of the algorithm, it means you're going to generalize better, meaning you're going to need a smaller training set to fit the problem to error epsilon, right? That's better sample complexity. And they further show that graph neural networks algorithmically align to dynamic programming algorithms. And dynamic programming, a general purpose strategy to break a problem down into subproblems and then recursively solve them and combine them, is a very general strategy which you can use for attacking many algorithmic problems. So this gave us even more encouragement to study GNNs in this light rather than some other neural networks. So this led us to our first paper in the area, Neural Execution of Graph Algorithms, which we actually concurrently published with that previous paper at ICLR 2020. And in this paper, we make a few very interesting but important observations. First of all, algorithmic alignment is a really powerful tool, but it really does not allow you to be reckless. Like, you cannot take the findings of what I just showed you and say, okay, great, I have an algorithmic problem I want to solve. I'm going to throw any random expressive GNN architecture at it and get good results. No, that's not going to happen. And the reason why it's not going to happen is because you're going to get not that good results out of distribution. And in the context of learning to execute an algorithm, you really care about how well you perform out of distribution. So what does this mean? Basically, when you sit down at a whiteboard and you write down a few graphs and you try to come up with an algorithm that you code up based on that, that algorithm will work no matter how big of an input I give you. Whereas in most cases, if you train a machine learning system at size 16 and then you try to run it at size 64, it's going to collapse drastically, right? It's just not trained to operate on those sizes, even though it was trained to execute the algorithm. So in the context of reasoning systems, any self-respecting algorithmic executor should be robust to changes in size, changes in distribution, and stuff like that. And that means if our model really learned to behave like the algorithm, it should work across a wide variety of inputs, not necessarily just the ones in your training set. And if you're not careful, any expressive GNN easily overfits to whatever specifics you have in your training data distribution. So you try to run it on a bigger graph, it collapses, or even worse, gives you numerical errors, right? So in our paper, we make several key observations on how to modify GNNs to make this problem a bit easier to deal with. And as a result, we're able to generalize to graphs that are 5 times larger at test time for 2 pathfinding problems. The first important observation is that usually when you apply graph nets or machine learning in general, you tend to have a stack of layers, right? And every single layer has different parameters. This is not a good idea if you want to do algorithmic reasoning, because imagine I need to multiply 2 numbers, right? The amount of steps I need to do increases as the numbers grow in size. But if you have a fixed number of unshared layers, you're limited by how many steps you can compute at any point in time, right? And this is also one of the reasons why if you ask modern day chatbots to solve a problem at various sizes, there's a certain size after which they start to hallucinate terribly, because they have no way of knowing that they need to change the number of steps that they're doing based on the input size, right? There are some hacks to get them to do this, but obviously not robust. So the only way that you can easily do this in a neural net architecture is to not unshare your layers, but have one processor network layer that is repeatedly executed for a certain number of steps. This now allows you at test time to run this processor network for as many steps as you need, okay? So that's the first insight we had. You should have a layer which is shared. The second one, this might seem obvious in retrospect, but GNNs, I mentioned, have this O+ operator, which aggregates all the messages together. I've told you the Bellman-Ford algorithm and many other algorithms optimize over the neighbors. So they have a min operator or a max operator. So really you should be using max as your O+. We had this observation, it led to huge improvements compared to say using the sum operator. And it might seem obvious now, but I must stress in the year 2020, we were going against the grain. We were really pushing against the folklore when we did this, right? Because there was a previous paper saying graph nets with sum are maximally expressive, max is strictly less expressive, so you should never be using max, right? No, that's not the case. I don't care about expressive power if it pushes together graphs which should be pushed together in the first place, okay? So in the context of learning to execute algorithms, using max turned out to be really critical. And nowadays we have solid theoretical evidence why this is the case. But at the time, this was very controversial. And the third insight we had was, rather than just doing the traditional machine learning, going from input to output, another way to line you up with the algorithm and get you to follow its instructions more closely is to supervise your model to predict not just the output at the end of the execution, but also all of the intermediate steps, because there's lots of interesting invariants happening in what the algorithm is computing, right? So say you're executing a shortest path algorithm like Bellman-Ford. It has this very nice invariant that after you run k steps of the algorithm, you should be able to find all the shortest paths using no more than k hops away from your source node. So what you can do is, after k layers of your processor GNN, supervise it to imitate the intermediate results of the algorithm. And this now gives you more closer guidance to what the algorithm is doing. And now these three combined together gave us a pretty big improvement in terms of out-of-distribution performance. But I must also stress that it's also a bit of a paradigm shift how we introduced these components one at a time and validated them. Because algorithmic alignment was not a new idea intuitively, not even in 2020. Like, there were lots of cool architectures that take inspiration from computer science. Perhaps the canonical example is the neural Turing machine and differentiable neural computer from DeepMind. Probably some of you have seen this paper. It was published in Nature in 2016, so it was quite influential. And in fact, it was so influential that in their efforts to imitate what an entire computer is doing inside machine learning, they invented one of the earliest forms of content-based attention. This was a year and a half before transformers, okay? However, nobody really uses neural Turing machines now. Why is that the case? Well, because they really tried to imitate everything all at once. And as a result, when things broke down, and they broke down immediately when you moved away from the carefully crafted problems they used in their paper, you couldn't really tell which component broke. Like, was it the content addressing? Was it the memory writing? Was it the highly intricate chaining mechanism? There were all sorts of things that could have failed, and there was no easy way to prototype which one failed, right? So our work is a bit of a paradigm shift. We still want to build something like a neural Turing machine, but we want to do so in a step-by-step manner, carefully introducing components, measuring algorithmic alignment. And you can keep playing this game starting from our paper. In fact, there's been a flurry of papers, many of which we have been involved in, that try to build machine learning models, graph neural networks that are better aligned to certain classes of algorithms. So you have shuffle exchange networks, iter GNNs, our own PGN that aligns with discrete data structures, and the persistent message passing, which even endows GNNs with extra auxiliary memory. And so it seemed like the general takeaway were you cannot just throw any GNN at any algorithmic problem. You should carefully craft the GNN to algorithmically align with what you want to compute. And this eventually led to more fine-grained theory. So the original algorithmic alignment theory was refined by the original authors to create linear algorithmic alignment. There were additional connections to the theory of causality and their own work connecting it to the theory of categories. So there's been a lot of theoretical work if you're interested in the foundations of how to build these models. Here are just a few references. And we are very actively working on some very interesting extensions. So watch this space. There will be more of these theoretical papers to come in the coming months. Now, hopefully this gives you an interesting overview of how we entered the field and this interesting question we studied of how can we get a model to execute a particular type of computation. But okay, let's get realistic now. Let's try to address the elephant in the room. Why not just run the algorithm? And you know, we had to address this elephant way more and way earlier than we hoped to, because while we have now a decent theoretical and empirical grasp on how to build a model that executes an algorithm better, you send this paper to a conference and you get reviews like this. What is the purpose of learning to do this? Why not just run the algorithm itself? My personal favorite, which I will quote to you. This paper will certainly accelerate research in building algorithmic models, and there's certainly a lot of researchers that would make advantage of it. I'm just not convinced this research should even exist, which is a really fantastic thing to read as the first author of a paper, right? It's just amazing, right? But okay, let's put my ego aside for a second and try to think about, is there a point to what the reviewer is saying? Can we maybe take away some lessons from it, right? Well, in some sense, there is a point to what they're saying, because tautologically, the target algorithm will always execute itself better than any GNN would ever learn over it. Like it's tautologically the most accurate. So now we couldn't keep thinking about this as just a curiosity-driven exploration. We really had to start thinking, can this actually be useful anywhere, right? And we came up with 3 ideas over the course of the past 2.5 years. For the remainder of this talk, I will present to you 3 ideas that, in my opinion, saw the most impact, okay? So let's start with the first one. Potentially, you know, I'm about to drop a bit of a bomb. So algorithmically aligned models accelerate science. And when I say algorithmically aligned models accelerate science, and you would like to see some evidence of that, as Pierre briefly mentioned, kind of killing my spoiler to some extent, if you want to have evidence of this, you should look no further than the cover of Nature. So this paper here was work that I have done together with several fantastic people at DeepMind and mathematicians at the universities of Oxford and Sydney, where we used these graph machine learning techniques and algorithmic alignment to help them uncover the structure hidden inside mathematical objects, which then allowed them to derive independently 2 separate mathematical breakthroughs in 2 very disparate areas of math, not theory and representation theory. And as a result of doing that, Nature has recognized the impact that we have done and published our work on the cover page. It also led to a reasonable amount of features in the press. But to be honest, these things are fairly inconsequential by themselves. What I really found to be the turning point were the anonymous reviews we got from the mathematicians who were reviewing our paper, right? So normally reviews are supposed to highlight the limitations of your work, tell you ways to make it better, and so on and so forth. In this case, the initial reviews we got from the mathematician were basically very much just straight up indicative of the impact. So this paper marks the beginning of a new phase in the use of computers in math research. I cannot imagine a mathematician not using these methods if they were available to them, because they would then progress much more slowly. And what I personally liked is that the 2 separate mathematical experts in the relevant 2 areas, not theory and representation theory, have judged our works as worthwhile of being published in separate top-tier mathematical journals. So there's 2 separate math papers hidden inside this Nature paper. And what I've been very, very happy about is that we have actually been able to do this since the publishing of this paper. And this specifically is a paper we published in the top-tier journal on representation theory, which details our findings to representation theorists, and already many people have built on it. For me personally, it takes a major item on top of my bucket list because it was always my dream to publish a math paper. I went to a math high school. I was surrounded by people who were very, very clever in maths. I comparatively wasn't that clever in maths. So this paper was a way for me to get myself on a very influential math paper without really knowing any math, which was pretty fantastic, right? And maybe gives inspiration to somebody else in the room as well. So how did it work? Basically, in this work, we take a GNN, we train it to fit some mathematical data set that the mathematician cares about, and then we use some simple gradient saliency method to tell the mathematician, hey, inside this complicated input that you care about, here are some parts, specifically in this case, the diamond structures that you might want to look at. Maybe these things will help you formulate your theory. And as you might imagine, it's much easier to analyze a small diamond with the naked eye than it is to analyze a huge graph like this. So naturally, this allowed the mathematicians to proceed and develop their theory. And shortly after, they developed this hypercube decomposition, which was somehow dependent on the diamonds, right? This was a step that they couldn't have easily made without the microscopic influence that the deep learning model had. And okay, so fit a GNN to a math data set. Once again, is it as simple as take any GNN and fit it to a math data set? No. As we discussed previously, you must be careful about which architecture you choose. And in fact, we got our best results when we took an algorithmically aligned GNN. So what this means is the mathematician gave us their insight and they told us, here is a formula that would solve the problem if I would give you some privileged information that you're not allowed to have to prove this theorem, right? And this equation, if you look at it, looks a lot like a graph neural network, but it's a very specific graph neural network. So we could make a GraphNet architecture which was aligned with what this equation was computing. And as a result, we were able to get good enough results to serve these results to the mathematician. So maybe a more general lesson here is that we have a target algorithm, but you cannot apply it. You can execute it, but it uses privileged information, so it's not useful for the theorem you want to prove. But you can use algorithmic alignment to take some priors from this algorithm and stick it inside your architecture and lead to mathematic discovery. So that's the first one. The second one, which I recently published with some co-authors from ETH at NeurIPS, is the idea that algorithmically aligned models are fast heuristics. Now, what do I mean by this? In this specific paper, we focused on the problem of configuring computer networks. I'm not a big expert in computer networking. I've only done like maybe a simple undergraduate course in this topic. But the protocols and setups of computer networking underlie the entire internet. So it's a really valuable and important topic to study. Specifically in this problem that we looked at, configuration synthesis, you have a set of specifications that are basically constraints for the routers in your network that they must obey for your network to operate smoothly. So your problem then is to take these specifications and figure out how to connect the different routers in your network such that when you run certain protocols, which are basically graph algorithms, you come up with this forwarding plane which is consistent with your specification. Now, this is a super, super hard combinatorial optimization problem. It is NP hard, and practically solving it requires using very slow SMT solvers, which are doubly exponential complexity in the number of routers and constraints, right? So really, really hard. So what we try to do here is invert the process, try to go straight from specification to configuration using an algorithmically trained graph neural network. So how do we make a data set to train a model on this? We have to basically, since we're going from spec to config, we need to have a way to invert our protocol arrow, right? And specifically how we do this is we start from some randomized topology, some randomized set of graphs that we sample from a distribution we believe is relevant for real world routers. We run the protocol to come up with the forwarding plane. And then we extract all the things that are true of this specification. So this gives us the constraints. And now we can train a model to try to invert this relationship. So to go from the specification to the configuration. Because this is a relationally specified thing, like a knowledge base, you can represent it as a graph as well. So this whole problem is basically filling the gaps inside a graph input. And when we train a system like this, because it's a simple forward GNN, naturally it's much faster than an SMT solver. And for simple, moderately sized problems of up to 18 routers, you can see speedups of up to 490 times compared to the SMT solver. So it's super, super fast. Of course, there is no free lunch. You get this speed up at the cost of accuracy. So it might produce assignments which are not correct or do not line up with real world specifications. So we set out to analyze how often does this happen? Like how often does it get a constraint wrong? And you can see even in the worst possible case, the average percentage of the constraints satisfied is over 90%, which, at least according to our computer networking collaborators, is already a really good level of consistency for human-in-the-loop use. And the reason why this is important is because even though you have this perfect algorithm that solves it in double exponential time, very often human design specifications are not good in the sense that they are unsatisfiable. You cannot find a satisfying routing configuration. So you've just spent doubly exponential time just to get the answer of no, I cannot satisfy this. So you're going to waste a lot of time being iterative anyway. So if you're going to be iterative already, you might as well use a really fast system that is mostly accurate and then use that to gradually refine your constraints. So in practice, this level of accuracy can be quite beneficial already. So more generally, in this case, a target algorithm is really tricky. We're only approximating it, but in such a way that it provides a fast and reasonably accurate heuristic such that humans can then use it and iteratively refine their networks. And lastly, we're going to talk about neural algorithmic reasoning, which was the area that I promised to you at the very beginning. I have outlined some of the general ideas that at least that we had in 2021 about this. So Charles Blundell and I co-wrote this position paper in the journal Patterns, which we used as a basis for some of this work. And it's a great place to start if you want to learn a bit more about this afterwards. So to get you thinking about why we need something like neural algorithmic reasoning, I'm going to prime your mind with a relatively simple example. Find me the optimal path from A to B, okay? Now, if you are a computer scientist, chances are you will see this question and you will react in a very, very singular way, right? At least I would. You would assume that I'm giving you some kind of weighted graph and I'm asking you to find the shortest paths in this graph. So naturally, you'll jump right in and implement your Dijkstra's algorithm and throw it at the problem, right? But hang on, there is nothing about this statement that tells you that I'm giving you a nice weighted graph with a single scalar on every single edge, right? In reality, especially if we want to solve real world problems, it's usually a picture like this. Like there is some real world, say, routing problem that depends on finding some kind of optimal path, but it's not given in this nice way, right? And I've personally experienced this when I worked on a team together with Google Maps to build a graph neural network to serve travel times. This is another one of my claims to fame, by the way. If you open Google Maps, wherever you are, you ask it to go from A to B, it will serve you an estimate of how long you will travel. That estimate is served by a graph neural network that I've co-developed with folks from DeepMind and Google. So what I learned there is that, well, as you might expect, the inputs that Google Maps works with are not like this. You actually take data from your phones. So your phones, they sit in your car and they move. And Google basically fetches the locations of the phones and based on the movement infers how fast traffic is going at any particular line of traffic, which is obviously not just noisy. You can move phones around in random ways to kind of mess up these measurements. It's also prone to adversarial attacks. Wonderful. You might have heard the story of a guy, I think in Belgium, who took 100 phones, put them in a sack and walked down the street like this, in the process convincing Google Maps to route everybody away from that street, right? This was a well-publicized adversarial attack. I think even Google blogged about it. So just to say, like, it's not just that the problem is loosely specified, people can tamper with the problem input, okay? So in this setting, like, there's no nice clear-cut way to go from the data you actually have access to, the dynamic data you have access to, and something you can apply the algorithm on, right? So normally, traditionally, this is done by humans. You either design a heuristic or you manually convert your data so you can run the algorithm. And this now begs the question, can we ever hope to manually do this mapping? I would argue that since the 1950s, we knew the answer to this question was no, but maybe we chose to ignore it. So here is a very nice paper from 1955, which introduces what is now known as the maximum flow problem. It's one of my favorite algorithmic problems. And in this paper, they used it in the context of studying the capacities of railway networks. At the very start of the paper, there's this very nice paragraph, which basically says, to estimate what are even the capacities of the railway networks, which you need in order to apply the algorithm. So you need to say there's a scalar on every edge saying how many trains can go down this line at any particular point in time. Just estimating those inputs is to a large degree an art. And even when you are, closely, intimately associated with the particular railway territory you're evaluating, the final answer and inputs you get is judgment and experience. It's more of an art than science, right? So it's been sort of known already back then that humans cannot really hope to do this mapping by themselves. And I think theoretical computer scientists, to a large degree, ignore paragraphs like these because they care about solving the nice abstractified problem. There's good reasons to do that. I'm not saying that's a bad thing, but we should also try to think, how do we bridge the divide back? How do we make all these nice abstract algorithms applicable to the real world that they were designed to help us solve, right? So there's a divide between algorithms and the real world tasks they were designed to solve. So what specifically is the problem is that if I want to satisfy these strict preconditions of the algorithm, it might mean I'm going to drastically lose information. And maybe put succinctly in one sentence, it doesn't matter that you can prove your algorithm is correct or terminates in a certain number of steps if you run it on the wrong data. It's as simple as that, right? And that's tricky even without considering things like your data being partially observable, there being an adversary with a sack full of phones and stuff like that, right? So what I'll try to show you here is how we can attack this problem. One possible way to attack this problem by what I like to call neuralizing the algorithm. Now, what do I mean by neuralizing an algorithm? Let's recall how we trained these algorithmically aligned GNNs before, right? So we have algorithmic inputs, we embed them into a processor GNN, we spin that GNN for a certain number of steps, and we predict some output like the shortest paths, right? This is something you can solve in abstract space with arbitrarily sized data sets. You can just randomly generate inputs and stuff like that, right? But once you've done this, you now have this GNN, which is a high dimensional to high dimensional mapping of the nodes in your graph, such that it somehow closely follows what the algorithm is doing in a latent space, in the sense that if you now have some simple decoding mechanism to go from this manifold to outputs, it can decode what the algorithm is doing, sort of. So it's a sort of high dimensional component that maps to what the algorithm is trying to do. And what that means is I can then stick it inside any neural network architecture in the real world over raw inputs that has to deal with some algorithmic components like this, right? So specifically, I can pluck out this processor network P that was pre-trained on the algorithm, and I stick it into any neural network that goes straight from my raw inputs to the outputs I care about, going through that representation in the middle. And this fixes a lot of the inherent problems about directly applying algorithms, because now I can learn through gradient descent what are the right inputs that I want to apply the algorithm. Everything stays high dimensional. So if my algorithm doesn't fit something properly, I can just add a skip connection to not go over the algorithm, and so on and so forth. So this is the blueprint of algorithmic reasoning, which was the centerpiece of our patterns paper in 2021. And as we say in the paper, it allows us to run these classical algorithms on inputs previously considered inaccessible to them. And I must stress, this was initially just a position paper, but now we have several proofs of concept that have shown this blueprint applied in various downstream tasks like reinforcement learning, self-supervised learning, and also neuroscience. Okay, and this is a small sample of the 4 papers that we have. I will now dive into the last one of those papers, the dual algorithmic reasoning, which was our recently accepted ICLR Spotlight. And specifically here, in this collaboration with folks from the University of Pisa, we try to analyze the brains of mice, okay? So you have an input, which is a huge brain vessel graph. You have the different veins, arteries, capillaries, and so on, transmitting blood. You want to predict which of these parts of the brain vessel graph correspond to which types of blood vessels. So what are the veins, what are the arteries, and so on and so forth. So you want to compute some segmentation of those nodes, right? Now, I am not an expert in mouse brain anatomy. I have no idea how this thing works. However, I sort of believe that the main purpose of blood vessels is to conduct blood flow. So if I had access to an algorithm that would be able to analyze the flow in this network, that might be useful for what I want to do, right? So let me pre-train a processor network to take a flow network and learn to execute max flow and min cut algorithms, which are 2 very closely related procedures. So you take a flow network, you run it through a processor, you predict these intermediate and final outputs, then you take that processor and you deploy it in a model that goes from the brain blood vessels to the segmentation. As a result, we get about 6 to 7% increase. So there's a representational advantage to using this pre-trained model compared to previous state of the art. And one thing I must stress is we trained it on max flow graphs of size 16. The mouse brain has 10 million nodes, okay? So it's 180,000 times larger graph than the one we trained that system on, and it still performed well. We haven't explored any careful ways to align these distributions or anything special. We just trained it once, deployed it once, and observed benefits immediately. No hyperparameter tuning. So I believe that if someone were to take our work and actually be careful about plugging the various components, you might see even more benefits. So if there are any neuroscientists in the audience, maybe this is interesting to you. But the dual training here was critical to this advantage. Training just on max flow or just on min cut was not enough, but training on both of them together is what gave us this representational advantage. Okay, so hopefully this gives you at least one interesting real world example of where this can be useful. There are more examples in the papers I linked, but now let's talk a little bit about, if anything I said so far sounds interesting and you might want to get in on the action, there's the question of where do we get good processors from? So while we might have a decent grasp now on why it's a good idea to execute algorithms, be it to discover new math or optimize heuristics or attack problems that algorithms couldn't reach, we still need to know which algorithms to execute. And that requires both domain knowledge and computer science knowledge. So you need someone in your team who understands, say, that this is a blood vessel problem that will depend on the max flow algorithm. And you need a computer scientist who will implement a data set for the max flow algorithm that you can train on. So what if you don't have any or either of those skills in your team? How can we reduce the barrier of entry to just any machine learning person who's interested? Or more generally, how can we have a good collection of processors that don't require you to know much about your problem? And to try to attack this problem, we turned to one of the standard textbooks in the area, the Introduction to Algorithms, or CLRS textbook. I hope many of you have seen this before. It's one of the gold standard textbooks for algorithms at undergrad level at university. And even though it's several thousand pages long, it only has about 90 algorithms in it. So when you think about it, the entire career of a software engineer is propped up on a relatively small collection of base skills that are then recombined. So if we could teach a model to execute all those skills, that can be a pretty solid basis to start from, right? And I must say, we haven't done the whole 90 algorithms. I'm sorry to disappoint. We only have 30, which is about a third. But still, those 30 algorithms span a wide variety of skills. We have a bit of sorting, searching, divide and conquer, greedy algorithms, dynamic programming, pathfinding in various graph algorithms, string matching algorithms, and even geometric algorithms. So there's a lot of things to choose from if you would like to teach a model to execute the procedures you care about. And what's great about it is it's publicly available. You can now go on GitHub and access our benchmark and train models on it. For a lot of the simple algorithms, you don't even need a GPU for it. Even a CPU will suffice. And we also have a companion paper, which we published at ICML last year, if you want to learn more about what the benchmark looks like. But this is something that can be played with immediately. And what makes our benchmark special is that we don't just generate inputs and outputs for these algorithms. We give you access to the entire trajectory, right? Because every two sorting algorithms do exactly the same thing, but it's their internals that make them special. So here specifically, you have a standard sorting algorithm, insertion sort, and we expose every step of the way how the predecessor pointers of this list change as it's gradually being sorted from 52431 to 12345. Right? And we have access to, we give you access to this already pre-processed in graph form, so you can immediately throw your favorite GNN at it and not worry about designing loss functions, encoders, decoders, all that stuff. The library is really more of a data set generator and a baseline generator than a data set itself, which means it's very easy to play with it or to add new algorithms or to modify existing architectures. So hopefully this gives you some interesting thing to think about if you want to benchmark how good your model is at algorithmic reasoning or deploying algorithmic models elsewhere in your future work. But now I want to raise the quick question of, can we use these algorithmic trajectories in more interesting ways? Specifically, if you remember, in our previous paper, I said we had this stepwise supervision where we imitated step by step what the algorithm is doing. And CLRS basically immediately exposes this mode of training. So by default, it will do this, right? Without you touching anything in the code. However, even though when we published our first paper, Neural Execution of Graph Algorithms, this was critical for good performance, by the time CLRS dataset came out, it largely stopped being useful. So there is this paper from Madavi and others from earlier this year that shows that if you don't do the stepwise supervision, you're actually going to do better than if you do it, right? And this is a bit weird because obviously we would expect it to be better if it follows the algorithm. Well, one likely culprit that made these results happen is the invention of what's known as the recall mechanism. It's a really simple trick that takes the input and feeds it back into every single step. So the problem was that previously, if you run a GNN over many steps, it forgets what the problem it was that it was supposed to solve. This way, you just remind it every step of the way what it needs to do, and that eliminates the need for stepwise supervision. Like, we only put it as an ad hoc method in CLRS, but since then, it's been thoroughly investigated by the paper from Bansal and others. I highly recommend reading it. It's really cool. They solve a maze partially, then they adversarially corrupt the representations, and the model with recall still learns to solve the maze from scratch, which is really cool, without any guidance to do so. So are there any other ways to make trajectories useful if stepwise supervision doesn't work? Well, there's a lot of interesting invariance and structure inside these trajectories. So here you have depth first search, which is an algorithm that every step of the way explores the smallest node that hasn't been explored yet, and it proceeds kind of in a recursive setting. So 1, 1 to 2, 2 to 3, it backtracks from 3 because there's nothing to explore, and now the next step is to explore 4 from 2. Now this next step, exploring 4 from 2, will still happen even if I transform the graph in many, many ways. If I add all of these dashed nodes and edges to the graph, that will still be the 4th step. Can we encode that invariance in a machine learning model somehow? And we can actually. We can define a set of nodes that are relevant to the current execution step, and we treat those as these green nodes, and everything else is kind of irrelevant to the current step. So in the case of, say, bubble sort, we only care about sorting the 2 items that are next to each other in the list. Everything else we kind of don't care for the current step. And we can use this idea to formulate, using the language of causal inference, a causal diagram for how the data of the algorithm changes. So which things it's causally dependent on, which things it's independent on. And this now allows us to define a regularization objective, which uses causal interventions. So specifically, we can do this contrastive loss in the style of the Relic paper, which takes 2 different versions of a graph that have the same trajectory trace. And you can contrast. So the blue and the green representations are the positive pair, and the blue and all these other red representations are the negative pairs. So you can do contrastive learning to force the model to follow these trajectories more faithfully from this point of view of invariance. And doing this turns out to be really useful. It's a paper we just published at ICML now, and you can see it's in the blue bars. It improves basically all of the algorithms up to 90% and higher. So it basically solves the out-of-distribution CLRS for a lot of these problems. And finally, if you compare no trajectory versus our method, it finally makes trajectories great again. So it's better than every single, almost in every single one of them. It significantly improves on the no hint performance. And lastly, I want to raise one interesting question, which is we talked about learning single algorithms. Why stop at 1? Since we have CLRS 30, could we learn all 30 of them? This was a very nice burning question for us. Also, we kind of promised we would do it. We were kind of pushed into it. Charles and I were giving this interview for VentureBeat, and the journalist decided to take some words out of context. And now you have this title saying that we're building one algorithm to rule them all. So now we had to deliver on this promise, right? So, but in reality, we built CLRS for this purpose in the first place, because now we map these 30 distinct algorithms to the shared graph representation, which means now we could potentially try to learn them together. So to have something like this, a single processor GNN that's capable of sorting, that's capable of pathfinding, that's capable of convex hull finding, and all the other 30 algorithms in there by having different encoders, simple encoders, then shared processor network, and then decoding the relevant results once again with simple decoders. Can we learn an architecture like this? Well, it's not as easy as it looks. Initial runs doing this naively led to NANs and numerical explosions all over the place. And there were even some prior papers like our very own NE++, which said this might not even be possible unless the algorithms are tightly related. But then we actually realized there were many tasks with high learning instabilities that cause all the other ones to break. So we instead focused on trying to improve our learning stability over single tasks. And we had like a 2-month mini strike where we tried many different ways to improve the models. And we ended up with this triplet GMPNN model, which very significantly improved out of distribution any previous method tested on CLRS. This includes transformers and MPNNs, by the way. So this was significantly better than all of those other approaches, both in terms of average performance across all the 30 algorithms, but also on how many algorithms they have over 90%, 80%, and 60% performance. And now that we had that architecture, now we did the naive multitask training. And now we had one generalist agent with performance in orange for the different algorithms, which you can see on some tasks, it's better than the single task specialist. On some tasks, it's worse. But when you take the average, which is here on the far right, they're basically indistinguishable. So on average, we have now one model, one processor that matches or sometimes even improves the 30 specialist models that were trained just on the algorithm and nothing else, okay? And all of the different things we introduced during our sprint help significantly. There's about 3,000 experiments worth of data on this slide that shows how taking away all the individual things we added to the model makes the performance gradually worse. So we took our paper, we published it as a spotlight at Log 2022. And if you want to read it, the link is here. So have we been reasonably successful? I will leave you with this interesting study that we very scientifically conducted on the website Reddit. So we went to Reddit r/singularity, and we wanted to see what some people were saying about our work. So let's see. It's not new, okay? Others have tried to solve it, but got some success. Our model has a lot more success. Yes, nice. Somebody thinks it's a pretty big deal, as they also have formal training in psychology, and they say it's close to one of our guesses to how a brain works. I don't really know that, but it sounds nice, so I'll take it. Remember how GPT-3 impresses us with fluent writing, but makes embarrassing blunders in arithmetic, basic logic, multi-step reasoning? This can be a way to incorporate algorithmic reasoning into models to reduce such blunders. I tend to agree with that. And my personal favorite, if you think of artificial general intelligence as a vehicle, you can think of Gato, the DeepMind multitask executing model, as the front seat. Perhaps our work acts as the side mirrors. They're all necessary components in the final car. Arguably, some are more important than others. So hopefully there's some interesting stuff that inspired you to learn a bit more after this talk. Obviously, there's a lot of stuff I couldn't cover in the space of 50 minutes. If you want to know more, we have a 3-hour tutorial just on algorithmic reasoning with tons of code examples, references, collabs, and so on. It's on this website, algo-reasoning.github.io, and you should find all the answers you want there. It's pretty relevant and still pretty topical. If you come from combinatorial optimization, you want to learn more, we published a 61-page long survey very recently on graph neural networks for combinatorial optimization more generally, and it's been published at JMLR a few weeks ago. And specifically, section 3.3 of this paper talks about algorithmic reasoning with comprehensive references. In summary, remember how I started this talk? It was an inconsequential, curious question raised by a competitive programmer. Where did we arrive? At something which in principle could be baked into an intelligent system and help us build some parts of the AGI of the future. No matter what your stance on the topic, I believe these methodologies will be very important and likely here to stay. And I'll be sticking around after the talk and for lunch if you want to chat more about NAR, its implications to AGI or otherwise, and please reach out generally. If we don't have a chance to talk today, you can also reach out via my email or via my various social networks. I must say before I conclude, it really takes a village. All of the papers I showed you here were published together with a lot of fantastic people from DeepMind, from Cambridge, from the University of Belgrade, from a lot of other amazing institutions. And this is just a list of some of them. They don't even all fit on this slide. So thank you to everyone. Thank you all for coming. I hope you enjoyed it.